Yeah, so let's go to the next talk.
Test.
From
Like that?
Yes.
Okay.
Yeah, from David Cornu at the Laboratoire d'études de rayonnement de matière en astrophysique. You must have a shorter title. Thanks very much. So I'll make a sound at 5 and 1.
Okay, thank you. So, hi everyone, I am David Cornu. I am a postdoc here at the Paris Observatory. So, oh, I need that.
Yeah.
So first I would like to briefly introduce what is the MINERVA project. So it stands for Machine Learning for Radio Astronomy at Observatoire de Paris. And it aims at regrouping several teams from several labs from the Paris Observatory in order to share knowledge, experience, and resources around machine learning methods for astronomy. So you have here the people from the MINERVA group, and you have in red the people with which we created a team in order to apply to the second SKA Science Data Challenge. So what is this challenge? So it's organized by the SKA Observatory. So it aims at detecting galaxies and extract their properties inside simulated SKA data products, SKA-like data products. So the objective for them is to prepare astronomers and to incite them to develop new and innovative data analysis pipeline. And our objective inside the MINERVA team was to adapt modern machine learning, especially neural networks, object detection algorithm, and to apply it to those astronomical datasets. So the first data challenge that was occurring 2 years ago was about finding galaxies in 2D images. And the second data challenge that just finished a few months ago was about finding galaxies inside an hyperspectral cube of H1 emission. So there are several networks that can be used, or architectures that can be used to perform object detection. We had a few examples during the week. So there are the UNets, which produce nice segmentation maps. We have the region-based neural networks, which are widely used because they are really accurate. And there are also the regression-based neural network, which are interesting because they are really fast and because they have a straightforward architecture that consider all this object detection problem as a big regression task. So this is what I will present today. So I will talk about the You Only Look Once network, or the YOLO network. So basically what it does is that it takes an image, it will subdivide it into a grid, and it will try to find possible boxes inside each grid element. So each grid element is a large vector with several possible boxes that are characterized by their position and by a size that is based on a box prior. So all this task is a large regression, and the output has the form of a large 3D cube encoding all the possible boxes inside of the image. And at the end, you will select the boxes that are relevant to your problem based on an objectness score that is given for each box. So I will have just a few words about the SIANA framework, which is a general purpose neural network framework that I am developing since a few years now, which is developed with astronomical applications in mind. So I will be really quick. The only thing I want to say is that it is already faster than some widely adopted frameworks on given neural network architectures. It is freely accessible on GitHub, and I will just answer 2 questions. Should you use it today? Maybe not, because there is still a scarce documentation and you might miss some of your favorite subtools inside it. But should you keep it in mind for later? Certainly, because we might get even better than widely adopted frameworks for a wider category of architectures. And everything you will see in the next slides have been implemented using this framework. So I will talk about the first data challenge to begin with. We didn't participate in this challenge because it was 2 years ago, but we used it as a training step in order to develop the algorithm and to port them to the second data challenge. So this challenge is defined by 9 images, but we will only use one of them, the one which is based on the lower frequency and the highest integration time. It corresponds to a 4 gigabyte image. You have an example of a subfield on the right. And it is provided with a 5% surface fraction with the appropriate label for the sources in order to train machine learning methods. So the objective of the challenge is to find the sources, to characterize each source and its properties, and to classify them. I will say no, that we didn't try to classify them, as all the team who participated in the challenge on time failed to perform this classification, so it doesn't matter that you try to do it, it's nearly impossible using these images. So here you have a glimpse of what is the network architecture we used for this challenge. So I will just summarize the most important parts. We have 22 layers, which correspond to 40 million parameters. We are using, as I said, a single frequency, so there is only single channel in the input. We have 8 box priors in each grid element of the YOLO prediction. And the most important thing is that we have modified the YOLO loss in order to predict additional parameters that are obtained in a regression fashion, which allow us to predict all the source parameters at the same time in a single forward pass inside this network. And as I said, we have no class prediction for this challenge. So the network is trained using Siena, and you can see that we have around 35,000 sources in our selected training catalogs, which is quite nice. And it takes between 3 to 6 hours to train on a quite beefy GPU. So the inference is interesting here because we are tiling the full image with a significant overlap, and the network is sufficiently fast to deal with this whole image in 30 seconds. So here you have some examples of the YOLO prediction. So the green box are the true boxes, and the blue box are the predicted boxes by the YOLO network. So I don't have time to analyze in detail what is working and what is not working in these images. The only thing I want to emphasize here is that you might notice that there is blue boxes around sources that do not have the green counterpart. It means that it's true sources, but those sources are below the selection threshold in surface brightness to achieve to be in our training sample. So those are real sources that the network managed to get, but it was not trained using this type of sources. So I will be quick about the parameter estimation because it's quite difficult to really emphasize what is working and what is not working. I will summarize it this way. So here you have example plots of predicted minus target, the relative difference between the predicted and target parameters. And everything that is between the two vertical red lines means that the challenge scorer gives us the total amount of points for this parameter. And what I want to say here is just that our source characterization is equivalent to other widely adopted tools characterizations, for example, GALFIT, and it is on par with other team pipelines. So actually, it seems to work really well. So here are the score we obtained. So I will take just a little bit of time to explain how the score works. So for an object that you have properly detected, you can get up to 1 point, depending on how well you characterize the source parameters. And if you have false detection, it will penalize by -1 point your final score. So again, we didn't participate in the challenge 2 years ago, but we take a few months to try this method on the first data challenge data, and apparently we would have crushed the leaderboard because we have much higher. And one thing that I want to emphasize here is that the profound pipeline is a non-ML pipeline, but the Claran pipeline is a machine learning pipeline which is based on faster RCNN networks. Okay, so now briefly about the second data challenge in which we really participated. So this time it is 3D data cubes, and you can see that it has attracted a lot of people. There were 280 participants spread in 40 teams. And this time the challenge is defined as finding the sources in 3D and characterize them, and there is no classification anymore in the challenge description. So again, here is a glimpse of our network. The important part are we are now doing 3D convolution. We have 23 layers, which correspond to 2.1 million parameters. We have only one single box prior per grid element because we have much few sources inside each subcubes. And we have, again, additional source parameters estimations. We train the network using SIANA. This time we have much less sources to train, only 1,500 sources. And it takes around 1 day to train on a quite large GPU. And then it takes 20 GPU hours to forward the full data cube. It might seem a lot, but it's mainly due to the fact that we have a high overlap between our subcubes, which helped us to maximize the score we wanted to recover, but we can achieve a good score already with much less overlap, so it can be much faster to forward on the full cube. Okay, so here are examples of what the network managed to detect. On the top, you have the brightest sources, the brightest source of the training catalog. So quite easy to identify, but those sources are not typical at all. The vast majority of sources are much more like the second one, the bottom one. And I don't know for you, but I am totally unable to identify a source there. There is just too much noise, but the network managed to identify them really well, and the vast majority of the sources that are identified just look just like that. Okay, so again, the problem is the same with the parameter estimation. It's difficult to characterize. It's the same thing if you are between the two red lines, you have the maximum number of points per parameter. The things I want to emphasize here is that it is really difficult to train this kind of regression on parameter using just 1,500 examples, but it seems to work pretty well, and we are on a pair again with the other pipelines. So I will skip that. It was just to illustrate that we developed two pipelines, and the best score was achieved by merging the two pipelines. And I will finish on the leaderboard. It's not to brag about the fact that we are in the first position. It's more about the fact that I wanted to emphasize that teams at every position in the leaderboard tried to use machine learning, and the best two teams achieve the best score with machine learning, but you can see that standard identification method not using machine learning like the SOFIA pipeline is really well placed inside this leaderboard. And I will leave you with the conclusion here, so I can take questions.
That's a super interesting talk. So essentially, just a general question again, so how do you assign a detection a confidence level to each of the sources that you find?
Inside the YOLO network, when you have a target box and the predicted box, if it's overlapping a nose, you will attribute it a probability of 1. And if it does not overlap any target box, you have a probability of 0. So just by running this process on several epochs, it will manage to pick up an appropriate probability between 0 and 1, because it's just a sigmoid activation here.
Okay. Okay. Do we have some questions from the audience? There's one at the back. State your name and...
Hi, my name is Natalia Korsakova. I have a question a bit related to that, but a bit different, because I'm working on gravitational waves, and I was curious with timing, like pulsar timing. They plan to use the SKA telescope, and I wondered, do they organize some data challenges on how you would observe pulsars for longer time and how you can time them in a better way? Because it seems that a lot of their problems come from pre-processing the data, choosing the best pulsars, etc. So I wonder what's the status there.
All right, so I cannot speak for the SKA, but I know that it seems that the future data challenges will try to get away a bit of simple object detection tasks. So it seems that they will want to have some different tasks to perform on SKA-like datasets. So it's not excluded that they will try to have a challenge that try to answer those questions, for example.
Okay. Okay. No more questions. We're out of time in any case, so thank you very much again.
Welcome.